Alright, in this video we're going to talk about graphing functions using transformations of graphs, and specifically we're going to talk about horizontal stretching and shrinking of a graph. Now there are a lot of different rules for graphing functions with transformations. This video is just going to focus on this one rule, the horizontal stretch or shrink, but please check out the other videos I did on the other rules of transformations of graphs, because you do have to know all of them in order to graph functions effectively, because each function might contain more than just one of the rules. Alright, so the way we get a horizontal stretch or a shrink, well, like you've seen, if you watch some of the other videos I did on those other rules of transformations, things that affect the horizontal direction are affecting the x value, so they're happening inside of the parent function, right? They're happening with the x, right? So for horizontal stretch and shrink, we are multiplying a number inside the parent function. That number is multiplying the x value, right? So to graph y equals f of c times x. Right, so it's not just f of x, it's f of c times x. Right, so if I'm going to graph something like that, if that number c is bigger than 1, then we shrink the graph of y equals f of x horizontally by a factor of 1 over c. Right, so before we even go into the rest of this, if you recall, if you watch the video that I did on the horizontal shifts, just moving a graph to the left or to the right, things that affect the horizontal direction tend to have the opposite effect of what you would think. Right, when we're doing a horizontal shift, we have numbers added or subtracted to that x. But adding a number actually moves the graph to the left, right? Subtracting a number actually moves it to the right. It does the opposite of what you would think it would do. And in that video that I did on those horizontal shifts, I kind of explained why it does that. Well, similar thing here. When we're multiplying a number times the x, you would think if you multiply by a number bigger than 1, well, that makes it bigger, and so that's going to stretch it out in that horizontal direction. It actually has the opposite effect yet again. Right, so multiplying by a number bigger than 1 actually shrinks the graph. Right, we don't multiply each x coordinate by c itself. We multiply it by the reciprocal of c, which is 1 over c. Or another way to think about it is, when that number c, whatever that number happens to be, is multiplying that x directly, to do the transformation of the graph, we actually divide all the x coordinates by c. Right, dividing by c and multiplying by 1 over c mean the same thing mathematically. All right, so if that number is bigger than 1, it's actually shrinking the graph by a factor of 1 over c. And if c is in between 0 and 1, if 0 is less than c is less than 1, then we stretch the graph of the parent function, the graph of y equals f of x, horizontally, also by a factor of 1 over c. Right, so if we are multiplying our x by a 1/3 or a 0.72 or something like that, that's actually going to stretch out the graph. If I multiply it by 1/3, it actually stretches out the graph by a factor of 3. All of my x coordinates would actually get multiplied by 3. Right? So when we're doing that horizontal stretch and shrink, when that number is multiplying the x inside that parent function, again, it has the opposite effect. Right? So if I'm multiplying by a number less than 1, it stretches it out. If I'm multiplying by a number bigger than 1, I'm shrinking it. And I'm always multiplying my x coordinates by the reciprocal of whatever that number out in front of that x is. Right, now remember, when you're graphing using parent functions, I probably should explain this before I got into all these rules, but this y equals f of x here, that's what we call a parent function. Right? There are certain functions like the quadratic function y equals x squared, or the absolute value function y equals the absolute value of x, and there's several other ones I made a video of where I explained what those graphs look like and some of the points on those graphs. But the parent functions are a set of functions that you should know what those graphs look like. You should know some of the points on the graphs. And then we do transformations of those basic parent functions to get the graphs of these other types of functions. And that's what transformations of graphs is all about. But it doesn't work unless you know what the graphs of those parent functions look like. So if you haven't seen the video I did on the parent functions, make sure you check that out so you have some concept of the parent functions that you should know and what they look like. All right, so again, when we do things inside of the parent function, right, when things happen directly with the x, well, they're affecting the x, which is the horizontal direction. Right? When I multiply inside the parent function, it affects the x coordinate, but it has the opposite effect of what you would think. Right? When I multiply by a number bigger than 1, I actually shrink the graph. A number bigger than 1 stretches it out. And we're always multiplying each x coordinate of the parent function times the reciprocal of the number that's in front of the x, which is the 1 over c. Right? Now I know that might not make much sense. Like, well, if I'm multiplying by c, why do I have to multiply all the x coordinates by 1 over c? I'm going to erase this now and put up an example. So when we do that example, I'll try to explain why we multiply by 1 over c instead of just c. Just like if you watch the video I did with the horizontal shifts left and right, I tried to explain there why adding a number actually shifts it to the left and subtracting a number actually shifts it to the right. There is a reason for that, just like there's a reason for this. It's a little counterintuitive, but once you see what the reason is, it'll hopefully make a little bit more sense to you, right? So I'm going to pause this and erase all this stuff and put up an example where we'll actually do one of these problems. All right, so here is the example of graphing a function using a horizontal stretch and a shrink. Actually, two examples up here. Right, so this one, if you watch some of the other videos that I did with the rules of transformations of graphs and saw some of those examples, this one's a little bit different from those other examples. This one, we're given the graph of some function y equals f of x, right? We're not given the actual equation for it. We're just told this is what the graph of y equals f of x looks like, and it's kind of like a sawtooth type function, just up and down, a bunch of line segments connected. You can see it's at 0, 0, it's at 1 half, 1, 1, 0, 3 halves, 1, 2, 0. It just keeps going up and down like that in both directions. All right, and from that graph of y equals f of x, we want to graph y equals f of 2x and y equals f of 1 half x. All right, so again, just like we saw a few minutes ago, when we have numbers multiplying the x inside the parent function, that affects the horizontal direction, and it's either going to be a stretch or a shrink. But remember, it's the opposite of what you would think. Multiplying the x value by 2 actually is a shrink by a factor of 1 half. It's a horizontal shrink. I should include that word horizontal. Excuse me. All right, so we have a horizontal shrink by a factor of 1 half. All right, so here we're doing a horizontal shrink. The vertical direction is not going to be affected here. So the graph is still going to go up and down between y equals 0 and y equals 1. Right? That's not going to get stretched or shrunk at all. It's going to get stretched or shrunk in the horizontal direction. And again, when we multiply by a number bigger than 1, we shrink it by a factor of 1 half. Or another way to think about it is, when I have that 2 times x, each x coordinate that I have in my graph is going to get multiplied by 1 half or divided by 2, right? Those two mean the same thing, right? So this point up here at 1 half comma 1, well, what's 1 half times 1 half? That's 1/4. All right, so this point is going to be 1/4 comma 1, right? The point 1, 0, well, if I multiply my x coordinate of 1 by 1 half, I get the point 1 half, 0, right? The first point here is 0, 0. If I multiply 0 times 1 half, that's still 0. So we're still going to be at the origin there, right? So I did the first 3 points. The next point at 1.5. If I multiply that by 1 half, I get 0.75 or 3/4. So that's going to be up here. If I take 2 and multiply that x coordinate by a half, I get 1. All right. So what my graph is going to look like here, it's the same type of graph. But it's all shrunk together, right? The up and downs happen twice as quickly here because of that horizontal shrink. And just to keep going with this in the other direction as well. All right, so that's what the graph of f of 2x would look like, and I hope you can see that clearly. It looks pretty good on the picture there. Right, so now, why does the graph of f of 2x, why is that shrinking it by a half instead of, expanding it or stretching it by a factor of 2? Well, look and see what happens. Right, to get this point here at 1, 0 for my original y equals f of x function, right, to get the point at 1, 0, well, if my x coordinate is 1, what number do I have to plug in here for x in order to make this be f of 1? Right, well, if I plug in x equals 1 half, 2 times 1 half gives me 1. Right, so plugging in a 1 half for the x here gives me the same output as plugging in a 1 for the x here. Right, if I plug in x equals 1 here, that's f of 1. On this one, if I plug in x equals 1 half, that's f of 1. Right, so in order that point there gets translated to x equals 1 half, and it shrinks the graph. Right, because that 2 is multiplying the x. To get the same x coordinate that I used here, I don't multiply the x coordinate by 2, I multiply it by 1 half. I hope that makes sense as far as what I was talking about there. To take another point just to kind of show you, right, on the original blue graph here at x equals 2, right, well, that was f of 2, right, I plugged in x equals 2. Well, what number do I have to put in for this x in order to make it f of 2, right? It wouldn't be 2 times 2, it wouldn't be 4, it would be 1, right? If I plug in x equals 1 here, 2 times 1 gives me 2, and I've got f of 2, same as when I plug a 2 into this one. Right, so that point at x equals 2, is now over here at x equals 1. It got shrunk by a factor of 1/2. Right? So hopefully that makes sense to you. That's the reason why when I multiply here by a number bigger than 1, it actually shrinks the graph. Because in order to get the same input from the original function, I don't multiply the x by 2. I don't plug in a 2 for x. I plug in a 1/2 for x. All right. So that would be my graph of f of 2x. It shrinks everything by a factor of 1/2. So the graph still has that sawtooth shape, but now it just goes up and down twice as often because I'm constricting it, right? I'm shrinking it down. For the second one, y equals f of 1/2 x. Right? So once again, that 1/2, that number multiplying the x is inside the parent function, which means it affects the horizontal direction, and multiplying is a stretch or a shrink. Right? So this is going to be a horizontal stretch. Right? Again, you would think, well, multiplying by 1/2, multiplying by a number less than 1, that would shrink it down. But actually, remember, the horizontal direction is the opposite of what you would think. So multiplying by 1/2 actually stretches it out by a factor of 2. Right? The reciprocal of 1/2 is 2. Right? So what's going to happen here? Well, my point at 0, 0, I can't really stretch that. If I multiply that 0 times 2, I still get 0. Right? Think about it like this. If I plug in 0 for x here, that's f of 0. Well, still, if I plug in 0 for x here, 1/2 times 0 is 0, and I still get f of 0. So plugging in 0 for both of these gives me the same output. Right? But what about for f of 1? Right? If I want to get f of 1, well, what number do I have to plug in here for x to make this be f of 1? Well, 1/2 times 2 is going to give me 1. Right? So my point here on my original blue function, right, the first one that I graphed, that point at 1, 0 is now over here at 2, 0. Right? It gets stretched out by a factor of 2. So instead of going up and down between 0 and 1, now it's going to go up and down between 0 and 2, and this high point here is going to be at 1. Right? If I take that middle point up here at 1/2, comma 1, right? Well, if I want to have f of 1/2, what do I have to put in for the x to make this f of 1/2? Well, that has to be x equals 1, right? Because 1/2 times 1 gives me 1/2. So this point here gets translated over there. This point that was here gets translated there, and the graph gets then stretched out in that x direction, in that horizontal direction. Right, so that black graph up there is the stretch, the f of 1/2 x. All right. So again, I hope that makes sense as far as why it's doing what it does. Like again, you would think multiplying by 1/2, well, that makes the number smaller, so it should shrink it. Multiplying by 2 makes numbers bigger, so it should stretch it out. But again, when you're dealing with a horizontal direction, things are the opposite of what you would expect because those things are affecting the x values. So in order to get the same x value from the original, it's almost like you have to solve for x. Right, so 2x here. If this was like 2x equal to something, and I had to solve for x, I would have to divide the 2 to the other side. Right, I'm actually dividing by 2, or I'm multiplying by 1/2. Right, if it was 1/2 x equal to something, and I had to solve for x, I would have to multiply both sides by 2. Right, so I'm multiplying everything by a factor of 2, and that's stretching the graph out. Right, again, that's the reason why these rules for the horizontal stretching and shrinking are what they are. All right, so those are the rules, or that's the last one of the rules. I already made videos for all the other rules of transformations. If you haven't seen those videos for the other rules, check those out. Of all the different rules for transformations, this is the one that you actually tend to see the least often. And to me, it's the most confusing one as well, so it's kind of good that you don't see it as often. But make sure you check out all the other videos I've done as well for all the other rules of transformations. Make sure you check out the video I did on the parent functions. And I think I'm probably going to do one more where I just kind of put all the rules together like a summary of all the different rules of the transformations of graphs and kind of see some of the similarities and differences between them. Because if you see the patterns and the similarities in the rules, it's not like 6 or 7 different rules you need to memorize. There's patterns there where there's only a couple things you need to remember, and then it kind of all fits together. Right? So make sure you check out that summary video that I'm going to do on all the rules of transformations.